This question is from GATE 2011 Mechanical Engineering paper, question number 42. A disc of mass small m is attached to a spring of stiffness small k as shown in the figure. The disc rolls without slipping on a horizontal surface. The natural frequency of the vibration of system is. Now in this system we can see that the disc is rolling. So let's assume it is rolling in a clockwise direction. If this is the initial position of a point, when it rotates, the final position now becomes this. So let's say point P was here. P now travels to this portion when the disc rotates by an angle theta. So we can take the independent variable or the degree of freedom of this system as theta. Now when the disc rotates by an angle theta, it also moves forward. So let's say that it moves forward by a distance x. If radius of this disc is taken to be r, we can calculate the forward movement x as we are taking the rotation theta to be very small. X is nothing but equal to this length of the arc. So we have x equal to r into theta. Now if disc is moving forward in translational direction by x distance, the spring will also be expanded by a distance of x. So when the point P rotates, the spring expands. The yellow colored overlapping position gives the configuration of the spring in tensed direction. So its expansion is also x. Now to calculate the natural frequency, we will form the equation of motion first, and we will use Lagrange's equation to form the equation of motion. Lagrange's equation is given by d by dt, partial differential of the Lagrange with respect to angular velocity theta dot, minus partial differential of Lagrange with respect to the rotation theta equal to 0. Lagrange here can be calculated as kinetic energy T minus potential energy V. Kinetic energy of the system is contributed by the disk. So we can calculate the kinetic energy by adding up the rotational kinetic energy plus the translational kinetic energy of the disk. Rotational kinetic energy of the disk will be half into I omega square, where I is mass moment of inertia of the disk, plus the translational kinetic energy will be half into mass of the disk into v square. V is the translational velocity, omega is the angular velocity. Let's substitute and find out this. We have half into mass moment of inertia of the disk is given by m into its radius square divided by 2 into omega can be written as theta dot whole square. That is angular velocity is the derivative of rotation theta plus half into mass into translational velocity v can be calculated by differentiating the translational displacement x. So x dot will be, r is a constant, differential of theta will be theta dot. So we can write in place of v r theta dot square of this. Let's simplify this. We have m r square theta dot square by 4 plus m r square theta dot square by 2. Adding the 2, we have t equal to 1 by 4 plus 1 by 2 into the numerator term. So it is 3 by 4 mr square theta dot square. Let this be 1. Now we will obtain the potential energy. Potential energy is by virtue of the spring. Because of the change in its configuration, it stores potential energy. So V potential energy is equal to half k x square. X simply is r theta. So we can write half k r theta whole square, which is nothing but k r square theta square by 2. Let's write the Lagrange will be 3 by 4 m r square theta dot square minus k r square theta square by 2. If we consider this 1 and 2, we have got from 1 and 2 the Lagrange. Let this be 3. Now using 3, we can form the equation of motion on the basis of Lagrange equation. So we have d by dt of differential of Lagrange with respect to velocity theta dot. So only the first term will come into picture. Its differentiation is 2 into 3 mr square theta dot by 4. So after dividing, we get 3 by 2. The 2 gets cancelled with 4 and gives us 3 by 2 mr square theta dot minus differential of this term with respect to theta will give us minus 2 times kr square theta. So we get kr square theta is equal to 0. Again, taking the differentiation here, we get 3 by 2 mr square plus theta double dot. Differential of theta dot is theta double dot plus kr square theta equal to 0. Now to find the natural frequency omega, we can use root over the coefficient of theta, that is k equivalent, divided by the coefficient of theta double dot, which is mass equivalent, m equivalent, which is equal to root over. Let's substitute the values. We have kr square divided by 3 by 2 mr square. So we finally get root over r square by r square gives us 1, 2k by 3m. 2k by 3m. This is the angular velocity, but we need to find out the frequency in hertz. So f will be equal to, omega is nothing but 2 pi f. F becomes omega by 2 pi. So we have 1 by 2 pi root over 2k by 3m. This is the natural frequency of the system in hertz. Let's go back and mark the correct option. So this answer is in option C. All the options are very close to each other. We'll have to mark it carefully. The answer is option C. Natural frequency of vibration of the system is 1 by 2 pi root over 2k by 3m. To learn more about Lagrangian equation, you can refer to the NPTEL video lecture 4, using the Lagrangian equation to obtain differential equations, part 1. It is from the course lecture series on dynamics of physical system. The course is by Professor Soumitra Banerjee. He is from Department of Electrical Engineering, IIT Kharagpur. I hope this solution will help you clear your doubt. Thank you.